Oh, hello everyone, my name is Philip and I'll be here as tech support during this tutorial. I want to introduce to you our tutor Vitaliy Pozdnyakov. He's a junior research scientist at AI RI and he will hold the model validation using deep generational stress data tutorial. So enjoy.
Yeah, okay, thank you. May I share my screen?
Of course.
Do you see my screen?
I do, everybody else should too, but if somebody doesn't, please type in the chat.
Yeah, someone. Could you confirm that my screen is visible? Okay, I hope everything is fine. Let's get started. My name, first of all, hello, my name is Vitaliy Pozdnyakov, and I welcome you to the tutorial on the topic of model validation using deep generation of stress data. You can open this notebook by QR code on the screen. Maybe I can somehow send the link to the participants.
Yes, I'll send now. Just give me a moment. It should be this.
I can send it to the chat, maybe.
It should be this.
Yeah, exactly.
Okay.
It's the right link to the GitHub, and in the main page in the GitHub contains the link to this collaboratory notebook. Okay, let's start. Our tutorial will be mixed format. We will combine between theory and practice. We will start with the theory about problem of dataset shifts. Then we go to the downloading and preparing the dataset for time series forecasting, because we will talk about the forecasting problem and how to estimate the robustness of forecasting models. Then we go to the practice about training and testing a simple LSTM-based model to forecast future time series data. Then we go to the theory about worst-case risk method, which helps us to understand robustness of the forecasting models. Then we go to evaluation the stability of our model. In our case, is LSTM-based model using the worst-case risk method. Then we will talk about time series generation, how it works. And then we discuss how it can be used for estimation of robustness of model. We generate the fake time series, which are similar to the real time series. And then we evaluate the stability of the LSTM-based model using the worst-case risk, but not on a test set, which we will done in previous steps, but on fake data. Okay, let's start with the theory about shifts in data. Consider a simple predictive model such as, say, some recommendation system. And in ideal world, we expect that dependencies that we were found in training set will give perfect result in the production stage. The basic hypothesis that underlies all machine learning models is that the training and testing data sets come from the same distribution, or at least a similar distribution. However, in the real world, we often face some challenges. First of all, data changes gradually over time, and sudden shocks, for example, COVID-19 or financial crisis, have an extreme impact of our models quality. And you may ask me, yes, indeed, models break if data changes, don't they? And to answer the questions to this question, let us introduce a definition of dataset shift. First, let us denote the model as F, and the input features as X, and the target as Y. It's a common notation in machine learning theory. Let us consider two types of dataset shifts. First is a concept shift, which is characterized by a shift in the conditional distribution of the target by the given features, while the distribution of features does not change. TR denotes the distribution on the training data set, and the TST subscript denotes the testing distribution. An example of concept shift is the spam filter, where the input features are some messages, some text, and the target is the spam label. When a new spam appears, a concept shift occurs because the conditional distribution of the target changes. To resist the concept shift, techniques such as retraining, fine-tuning, and online learning are commonly used. And but we not go to the details in this tutorial. We will talk about covariance shift. Covariance shift is a shift in the input features, while conditional distribution of the target does not change. An example is disease diagnosis, where the features are some medical data, and the target is disease status. A shift may occur when the model is tested in a different hospital, for example, where doctors may use different approaches, such as performing different medical analysis. That is, there is a covariance shift because the dependencies of target, our target, which is disease status, with respect to input information, remains the same. In the picture, you can see an example of covariance shift and concept shift in synthetic data. With the covariance shift, we see that blue dots is on the left side and the orange dots is on the right side. However, the spread on the X2 axis increases. With a concept shift, we see that the orange dots is now in the center, while the blue dots are on the edges. The phenomenon of shifting in data often occurs over time and is found in many domains. For example, in photos of people, or satellite images, or in medical data, or in news articles and scientific publications. you can read more about this problem in this scientific paper. In our tutorial, we will learn how to estimate the robustness of model to covariate shift using the worst case risk method. And then we will see how we can refine this estimation using generative models. Okay, let's go to the practice. In our tutorial, we will use the auxiliary library, which we have specially prepared for this tutorial, and the genrisk library, which allows us to evaluate the stability of models. You can install this library by yourself and check the stability of your models after our tutorial. Okay, let's import everything. Our data set represents weekly data on gasoline consumption in the United States, and here you can see the date, which represent weekly changes in the consumption of gasoline from week to week. And we will use the first 17% of the data for training period and the last 30% for testing. Let us see how it looks like. Here's the changes of consumption of gasoline, and the orange line represents the split between testing period and I'm sorry, training period and testing period. In addition, we will use some covariates, which we can use as additional information to improve our prediction. In our tutorial, we will use simple positional encoding from the week number of over the whole year. For first value, this positional encoding, we is the sign of from 0 to 2p, and the second part is the cosine from 0 to p also. And let's take a look at the visualization of the covariate function. Yeah, there are here our covariates. Let's divide our target and our covariates into train and test sets. Okay, also we make some standard techniques like standard scalar, which reduce the dispersion of our input data. Any questions so far? Okay, I hope everything is clear. Let's move on. Today we are going to check the robustness to the dataset shift of the LSTM-based model. The main feature of this model is that we use past forecasting values for make a prediction to the next forecasting values. The letter Z denotes the covariates, which we know in advance. The dotted line represents the separation between input sequence and the forecasted sequence. And here we see that the first steps we produce forecasting for past values. And after the dotted line, we use forecasted values from the previous step to give the prediction to the next forecasted values. We will not waste time on training the model, so we will download the pre-training model. You can check how the model is trained after our tutorial, for example. Okay, let's do this. Download the model and read this model. Okay, let's look how our forecasting looks on the testing period. Here we pass the forecasting horizon. Then we pass training target, training covariates, and test covariates because we know them in advance. Of course, forecasting 9 years ahead does not have much sense. So the backtesting procedure is usually used in this sort of forecasting models. The main idea under the backtesting procedure is we create a sliding window and fed data into the model into a historical order, and we divide each window into 2 parts. The first part is used as the input sequence, and the second part used for produce forecast. And we calculate the error between the prediction and the real values in the second part of our window. Here's the backtest method, which takes as input our model, input size, horizon, target, and covariates. Then we use past target, past covariates, and future covariates to predict future target. We accumulate the error on the last value from the window. Here's the last value. And the backtesting method returns a list of errors for each forecast data. For our forecasting problem, we take the entire size, input size as 10 weeks, and the horizon as 100 weeks. Here the calculation for the obtaining error, and we can see that average value of error is around 0.24, 0.25, and the full data set with error looks like as follows. So for each date, we have the error value. Okay. Any questions? No. No open questions. Okay. How to estimate possible risks? The idea is following. Often some variables may change, while others remains the same. And unchanged variables save their distribution during shift in the data. Let us denote the variables that can be changed as W, and they are called as mutable variables. And the variables that can be changed, unchanged as Z, capital Z, which we call immutable variables. Then the full distribution of input features can be factorized through two distributions. First is the conditional distribution of W over Z, conditional distribution of mutable variables over immutable variables. And the second distribution is the distribution of immutable variables only, distribution of Z. And in this form, we can see that the distribution of W over Z changes. Here's the original distribution, and this is the shifted distribution, while the distribution over the immutable variables remain the same for original data and for shifted data. Here's the introduction of the worst case risk method, which allows us to estimate the potential reduction of model quality. Reduction when there is a shift in the data. To do this estimation, we follow several steps. First step, let us find the small sample size, find the small fraction of the original data at which the model shows the worst quality. The second step, let's make sure that the distribution for the immutable variables has not changed. And finally, we will call the quality of the model on such worst subsample as the model risk. The smaller the fraction, the smaller the sample size, the higher the risk we obtain, and vice versa. We denote the subsample fraction as 1 minus alpha. And in order to perform these steps, we use two models. The expectation model estimates the error of our target model, which is LSTM-based model, on the mutable and immutable variables, both of them. While the second model is the quantile model, which estimates the quantile of the LSTM model error on the immutable variables only. And then we can estimate the worst subsample by comparing values from the expectation model and values from the quantile model. If the expectation model returns the greater value than the quantile model, we assign such an example to the worst subsample. This picture shows an example on synthetic data. On the left side is the error on the some test data. Here's the some input features represented by x1 and x2 axis, and the target value represented by the color blue and red. And in the center, the error on the 10% worst case subsample is much larger error, while the variable x1 is unchanged. We can see that the distribution over x1 approximately the same as in the original data, while the significant data set shifts is visible in the x2 variable. So x2 is mutable variable and x1 is immutable variable in this case, in the center of the picture. Let's look on the right. The same fraction of the data, only 10%. We can see that the error also much larger than the original data, but not as large as in the previous data set shift. Because here we define our immutable variables as x2, and we can see that the distribution over x2 approximately the same comparing with the original data, while in the distribution over x1 have been changed comparing to the original data. Here the main idea. For more details, you can read this paper. Let us create a data set to assess the robustness of our model and select the variable and which are mutable and immutable. We again use a sliding window within which we count the difference between the last value and the lagged values. Here we use some predefined number of lags. Let's just look on the final data set. Here the difference between the last value in each sliding window, between the last value and the lagged value on 1 step ago, and 2 steps ago, and 3 steps ago, and so on. And the last 2 columns are our covariates, which are positional encoding. And for our problem, it's logical to use difference between the last and the lagged variables as mutable variables and the covariates as immutable variables, because we don't expect the change in our covariates because it's just simple positional encoding. Here the list of mutable variables and immutable variables. We will estimate the worst case risk at different levels of alpha. Alpha is represents the level of our risk from 0.1 to 0.9. For each alpha, we will keep the we will store the risk value and 95% conditional confidence level, confidence interval. And let's see what the estimation does in the code in our GenRisk library. Here the conditional model. We can see that expectation model and quantile model are gradient boosting regressor, and we divide our input data sample into several parts, and iteratively estimate the error expectation and the quantiles and expectations, and we assign Yeah, we assign the mask to the mask. The worst sample those values whose quantile is greater than the expectation. Oh, sorry, expectation greater than quantile. Okay, let's calculate our risk values. Here the risk values, here's the lower bound of our risk, our confidence interval is, and this is the upper bound. Here we use as input our input data set with mutable and immutable variables, and the list with error. So our conditional model can train expectation and quantile model to predict the expected value of error and quantile value of our error. Let's draw the estimated error at the different levels of risk. And we can see that as the risk level increases, the error also increases. We can see the green line. And by x-axis, we see risk level, and by y-axis, we see mean squared error. Additionally, we can draw an example that fell into worst subsample, which we call just stress data which contain it in the worst subsample. Here's our mask, which represent the indicator function shows which example assigned to worst case subsample. Here's true in each places where there is worst case subsample example. Yeah, here's the stress data for our model in the highest level of risk. Just only one of them. We select the first one. Just index is 0. Limitations of the worst case risk method, sorry, is two points. The first one is high uncertainty for the high levels of risk. We can see the high confidence interval here. And the second is not all shifts are represented because we use only test sample, and the test test set is strictly limited. And our suggestion here, sorry, let's generate data to model new covariate shift, which we cannot see before in the train set. Okay, any questions so far? Is everything clear? Okay, I hope so. Let's move on generation of our data set, our time series data. And first, a word about the difference between discriminative and generative models. Discriminative models learn a conditional distribution of a target from given features. by a given features. For example, we can imagine the feature that is a photo of some animal. We have two types of photos, photos of cats and photos of dogs. And the target is the label, which we need to predict. Is it a photo of a cat or is it a photo of a dog? And we can think about the discriminative models as the finding a dividing line between these classes of dogs and classes of cats in some latent space, some vector spaces. On the other side, generative models learn the full joint distribution over targets and features. That is, it generalizes vectors in the vector space into a complete distribution. And knowing this distribution of the data, we can sample data that was not in the training sample. And there is an example. One type of generative models is deep generative models, which actually means that deep generative models use neural networks inside the generative models for generation. Yeah, and the principle of these models is as follows. Let us imagine that we have some latent space, usually of low dimensionality, described by some simple distribution, for example, Gaussian distribution. And it's easy for us to sample from this distribution. On the other hand, we have a data space, which is usually multidimensional, has a complex dependency, complex distribution, and is really hard to understand how to sample from this distribution. And between them, we have some neural network that translates vectors from the latent space into the data space, so that they looks like real data. This neural network is called a generator. I want to talk about generative adversarial networks because it's a very popular method for generating time series. We call generative adversarial networks just as GAN, and the GAN is represented by two neural networks, a generator and a discriminator. The generator translates a vector from the latent space into time series, similar as with images. And the discriminator evaluates whether the time series is fake or is real. During training, the generator learns how to create realistic examples of the data. And the discriminator learns to detect fakes. Both neural networks compete to each other. And because of this, the quality of the generation is improved. In our tutorial, we will use GAN on temporal convolutional network, or simply TCN. Is the architecture of neural network that translates one sequence into another sequence with the same length. I mean, input length and the output length are the same. And the advantages of TCN is three advantages, main advantages. First is exponentially large receptive field. It means that you can cover a very, very long sequence just in a couple of layers. Second is that TCN can be used for a sequence of arbitrary length. It's doesn't depend of length of input size. And in addition, a special kind of convolution allows us to efficiently use the temporal dependencies in the time series data. We will use TCN for both the generator and the discriminator. In the generator, the number of input channels corresponds to the size of the latent space. The number of channels on the hidden layers represents some large number that allows us to consider a long sequence in the data. And the number of channels on output layer is the dimension of the time series data. And in a discriminator, the number of input channels corresponds to the dimensionality of the time series. The number of hidden channels, they're same in the generator, and the number of output channels is 1 because we need to predict the probability that is only single number from 0 to 1, where 0 is real data and 1 is fake data, or vice versa. It's doesn't matter. Okay, we will use both targets and covariates, but we use the covariates only for conditioning our generative model. So actually, we will generate only target time series. Here we combine target and covariates for training our generative model. Here are some hyperparameters of our generative model, which can be fine-tuned by some search strategies like grid search or random search. Now we can start to train, but we want to start train our model, but we skip this part because we don't waste time to training the neural network. The important part here that we use the test data to train our model, because we are modeling shifts in the data that close to the test sample. We are looking the shifts in test data, and then we, because of this, we train our model on only test data. I want to notice that GAN is a really unstable model because the generator and discriminator are constantly competing with each other. And during training, I highly recommend to monitor additional metrics such as Kolmogorov-Smirnov distance or Earth moving distance to understand when we need to stop training our generator and use it for samples, new data. Here we download our model. And the next part is evaluation of generated time series. Our task is to evaluate how well the generative model has been trained, and there is still no universal evaluation standard so far. So we will consider several approaches to do this. And the first is a simple visual analysis. Let's draw a time series, real and fakes, and compare them visually. We can see that the fake data, which represented by lines of different colors, replicates the spread and seasonality in the original data. In addition, we know that they have sufficient diversity to help us for modeling different covariate shifts. Now let's compare data distributions. In time series, usually not the absolute values of time series are compared, but the first differences in order to isolate the influence of trend and seasonality. Yeah, here's the histogram of first differences between on test data and fake data, and we can see that real and fake data have a very similar difference distribution. In addition, we can compare the autocorrelation functions. Again, we see that, wait a minute. Yeah, we see that they are similar in the sense that the first values are the same, and the subsequent values are near zero. Here, the approximately the same autocorrelation values in the test data and the fake data. The second approach is a statistical test, some statistical testing. And the simplest way is the Kolmogorov-Smirnov test. If the value of p-value of this test is less than 0.005, we can conclude that the data are from different distributions. Let us run the cell. Yeah, we can see that it's higher than 0.005, but it's in the some border lines between the statistical testing. And the third, the last approach is a comparison with some baselines. Let's compare the partially autocorrelation function between real and fake data. And then let's compare partially autocorrelation function between real data and just only random noise. Here the error, here the error between test and fake data. And then we compare it with the just random noise. Yeah, we can conclude that in general, the fake data is similar to the real data. And conclusion at this moment is follows. So we split the data set into train and test. Then we train it GAN model on the test data set, since we're looking for shifts close to the test data. And then we created fake data and checked that it's quite similar to the real ones. Okay, any questions so far? No questions. Okay, it's quite scary. No questions. Hope everything is clear. I don't know. Okay, let's do the last part of our tutorial. We will talk about fake data in terms of property of the distribution. Generative models have the property of generalization. That is, they can generate probable examples that were not in the training training set. And we can use this property to model covariate shifts in the data. The image shows the general process of using generative models to model shifts. First step, we create fake data based on the test sample. And the second step, we estimate the worst case risk on the fake data. So everything is the same as in the previous step, but we use the fake data instead of test data. We again backtest the model on the fake data, but first we need to create fake data. Here we create our covariates, which we know in advance. We will use a fake sample size 5 times larger than our test sample. And then we create fake covariates and fake target using our GAN model. Then we again backtest the model on the fake data. Let's wait 1 minute. Okay, we can note that the quality of the model on the fake data is approximately the same as on the test data, which once again shows us that the fake data are similar to the test data from the point of view of our target model. Then we again specify mutable and immutable variables and estimate risk in the same way as we did for the test data. Here the input data set, which the first 5 columns we use as mutable variables and the second 2 columns as immutable variables. Let us estimate the risk values. and compare the results. Let's compare the results. Yeah, and we can note that we were able to reduce the spread of the risk values. It means that we refine the risk assessment with the help of fake data. We can see that green line is fake data, blue line is test data. We can see that both of them increases with increases of risk level, but the fake data have more narrow confidence interval for the risk value. And finally, we can look at the fake stress data, which we again use the mask, which stored in the conditional shift model. Yeah, this is our fake data, which were classified as stress data and be included into worst case subsample. And at the end of our tutorial, I want to discuss some challenges of this procedure of evaluation of model robustness. First of all, generative models can produce realistic data, and this can help us estimate the model robustness to the dataset shift in precisely covariate shifts. But there are some challenges, and the first one is it's hard to find the best parameters of our generative model. And some generative model like GAN is hard to train, hard to understand when it should be stopped and used to generate new data. The second point is hard to estimate how close fake time series to the real ones. No scientific standard so far, so we can use different approaches like visual analysis, like statistical testing, and like comparing with different baselines. And the third one is the most important one, is that underlying hypothesis here is we assume that the generative model can generalize original data distribution and can really sample realistic data to model new covariate shifts which did not encounter in the training set. And so conclusion for our tutorial, we have learned what is dataset shifts. Then we learned how to prepare dataset for time series forecasting problem. We learned how to train and test for forecasting model for an example of LSTM-based model. Then we learn what is the worst case risk method and how it works. Then we learn how to evaluate the stability of the model, again in the example of LSTM-based model using the worst case risk on the test data. Then we learn what is the time series generation and how to generate fake time series which are very similar to the real time series, and how to compare, how to evaluate quality of the generation. And finally, we learned how to evaluate the stability of the forecasting models using the worst case risk based on fake data. That's it for today. Thank you for your attention. I will be happy to receive any feedback from you. Feel free to write me on the email, which you see on your screen. And goodbye. See you on the offline part of our conference.
All right. Thank you, Vitaliy. That was very interesting. And thanks to everyone who participated in the tutorial. Goodbye, everyone.
I see the question.
Oh, there is a
Everything
question.
was clear.
Oh,
Yeah,
okay.
thank you. Thank you so much. Thank you. Bye.
Bye.